Hello everyone and welcome to today's presentation. We are going to explore two prominent numerical methods used to approximate definite integrals. First, the trapezoidal rule, and second, the Simpson's one-third rule. Both methods are essential when solving integrals that cannot be solved easily with elementary function. So first, let's look at the trapezoidal rule. This rule approximates the area under the curve by breaking the interval into small subintervals and using trapezoids to estimate the area. Let's try to visualize what just being said now. So let's look first the trapezoidal rule and try to visualize what it is. So let us assume a function whose graph is given like this. What trapezoidal says that we divide the area under the curve into n equal parts. From let's suppose from x1 to x6. So we divide the area under the curve into 5 equal parts, and we try to estimate this area using a formula given as let's give this x2, x3, x4 and x5. So according to the formula of trapezoidal rule, it is given as a b f of x. Here f of x is any function given as h by 2 y0 plus yn plus 2 into sum of all the terms plus yn minus 1. Here let's see into the variables. Here a and b are the limits of integral, a being the lower limit and b being the upper limit. Here h is the size of the subintervals between a and b, and which is given by b minus a upon n, and n being the number of intervals we are taking from x1 to x from our upper limit to lower limit. Here let's take this example. Here n will be 6 because we are dividing the area under the graph in between and high. So this is how h is given, b minus a upon n, and n being the number of sizes we are taking under this area. So h is equal to b minus a upon n. So let's look into one of the examples to understand better the trapezoidal rule, and then we will be solving the same problem with Simpson's one-third rule. So let's first look into from trapezoidal rule. So here our function is given integration 0 to 6 dx upon 1 upon x square, and the values for each intervals is given in this tabular form. So in this problem, we will be solving this problem by taking in 6 equal intervals. So if we take 6 equal intervals, our s will become 1 as by the formula h is equal to b minus a upon n, and we have decided to take n is equal to 6. So h will be b being our upper limit 6 minus a being our lower limit 0 upon n, which we decided to take into 6 equal parts. So it will be 6 and h will be 1. So as you can see here, h is going to be 1. So from y0 to y6, we will be dividing our 0 to 6 limit into 6 equal parts, and we have to find the corresponding values of each interval. And as you can see, the same is given in this tabular form. So according to trapezoidal rule, to evaluate a function, we have upper limit a limit b fx dx is equal to x upon 2 y0 plus yn plus 2 into y upon y1 plus y2 plus 1 plus y upon n minus 1. And here y0 being f of a and yn being f of b. Here we have a is equal to 0, b is equal to 6, and f of a, or you can say f of 0, is given here, which is equals to 1, and f of b, which is same as f of 6, and which is given as 0.027. And correspondingly, there are we have a value of y1, y2, y3, y4, and y5. So let's try to visualize this problem. Here the function, let's suppose this is the function where we have x, where somewhere here it's 0 and here it's 6, and correspondingly the values are given, and we are said to divide this area under the curve into 6 equal parts, and each size having one h is equal to 1. So 1, 2, 3, 4, 5 and 6. So let's try to evaluate this problem, which will be given as 0 to 6 dx upon 1 upon x square will be given as, here h we have taken as 1, so 1 upon 2 y naught being f of a, and which is equal to 1. So let's first try to write this equation. Plus 2 y1 plus y2 plus dot 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 yn minus 1. Here n minus 1 is y of 5. So let's just put values. So y of 0 is 1 plus y of n is 0.027 plus 2 into y of 1 is given as 0.5 plus y of 2 is given 0.2 plus 0.1 plus y of 4 is given as 0.058 plus y of 5 is given as 0.038. So after evaluating this, we get a final answer of 1.14. So that's it. Now let's move on to Simpson's one-third rule. So before starting, there are two rules for Simpsons. First one is Simpson's one-third rule, and the other one is Simpson's three-eighth rule. In this video, we are going to see only for Simpson's one-third rule. So let's move on to Simpson's one-third rule. This rule is a bit more sophisticated than Trapezoidal rule and provides a higher degree of accuracy by approximating the curve using parabolic segments instead of straight lines. As we understood that Simpson one-third rule uses parabolic analysis to give its result. So now let's look into its formula, working formula, and which is given as integral a to b, any function given to us at x dx is equal to x upon 3 y naught plus yn plus 4 into all the odd numbers of term yn plus dot 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 yn minus 1 plus 2 into even numbers of terms given as plus minus yn minus 2. Uh, Here same a is the lower limit, b being the upper limit of the integral we are taking, h being b minus a upon n which we decide in how many equal intervals we want to break our area under the curve. Here y naught being f of a, yn being f of b, and the corresponding values of intervals which are taking, to that we get y1 plus y2 plus y3. And so we are taking equal intervals, so we can also represent our corresponding values as y1. Let's suppose we take an example of y1. So y1 can be given as the value of x naught plus h. The value of x naught plus h we get is that of y1. So let's move on and see another example. Y2 can be given as x2 plus 2h. What this simplifies is that we are taking equal intervals x naught plus and h. So this proves that we are taking equal intervals for our area under the curve. Now let's look into one of the examples. Which we previously solved in trapezoidal rule to get an idea that as we go further and further, we get more accurate to our answer. So let's look into this examples. So here we are also said to divide our area under the curve into 6 equal parts. So again we are taking our h is equal to 1, which can also be found by the formula h equals to b minus a upon n. Here we decided to divide our area under the curve into 6 equal parts. So here n is equal to 6, and as given in the equation, b is 6 minus a, which is given as 0 upon n, which is fixed as 6. So this gives us x equals to 1. Now let's put these values in our formula, and what our formula says is that 0 to 6, here our function is 1 upon 1 plus x squared dx is equal to h upon 3, y naught being our f of a value, of whose values we are going to find from this given table, y plus n minus 1 plus sum of all even terms y2 plus y4 plus y n minus 2. So let's put the values from the table. Here h is equal to 1 upon 3, y naught being 1, yn being 0.027 plus sum of all odd terms 0.5, y3 is equal to 0.1, and y5, as we are going only up to 6, so our last odd term will be y5, and it will be given as 0.0385 plus sum of all the even terms y2 plus y4 value is given as 0.8, and after solving we get a value of 1.36. 662. Now let's try to analyze the answer for same question, for the different answers we got for the same question. By using trapezoidal rule, we using trapezoidal trapezoidal rule, we got the answer for our function, which was 1.4108, and by for solving the same question using Simpson's one third rule, we got an answer close to 1.3662. So now let's find the percentage of error, or can say the more accurate value, by using our traditional way to solve any differential equation, definite integral. So let's solve it. So now let's try to solve our given definite integral using our traditional method. So solution, as we know, integration of 1 upon 1 plus x squared dx is given as tan inverse of x. So let's try to put this into our problem. So given integral dx upon 1 plus x squared can be written as tan inverse of x, upper limit 0, 6 to lower limit 0. So let's try to evaluate this, and we will get our answer in radians. So this can be written as tan inverse of 0, and which answer is nearly 1.38, so on so on. So now let's analyze the results we got from different methods. So first, using trapezoidal rule, we got an answer approximate to 1.41, and using Simpson's one-third rule, we got an answer which was close to 1.36. So as you can see, Simpson's one-third rule gives more accurate value, uh, which is uh, which is near to the original value which we got from solving using traditional method. So so as we go further and further in Simpson's 3/8 rule or 5 upon 12th rule, we get closer to our answer. That's a brief overview of trapezoidal and Simpson's one-third rule. We can say that both are powerful methods for numeric integration, and each has its strengths depending on its situation. Uh, and if you are dealing with a smooth function and need a precise result, Simpson's rule is likely the best method you can go with. So we can conclude that Simpson's gives more accurate values as compared to trapezoidal rule. And that's for our presentation, uh, for trapezoidal and Simpson's one-third rule. Thank you.